Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe the concept of a standardized relation between two variables, a correlation. You may want to know how one continuous variable changes when another continuous variable changes. For example, take two continuous variables, height and weight. You might want to know how weight changes as height increases. For example, as height increases, does weight increase or decrease? A linear correlation tells us the degree to which a straight line describes the relation between two variables. Not all relations are linear, of course, and I'll give you examples of nonlinear relations later. A correlation coefficient gives you two major pieces of information. The first is the direction of the relation. The second is the strength of the relation. Linear correlations range from -1 to +1. In other words, the lowest a correlation can be is -1, and the highest a correlation can be is +1. The sign of the correlation coefficient, that is, whether it is positive or negative, tells us the direction of the relation. A negative correlation means that higher scores on one variable are associated with lower scores on another variable, and lower scores on one variable are associated with higher scores on another variable. Sometimes people call negative correlations inverse correlations. A positive correlation means that higher scores on one variable are associated with higher scores on another variable, and that lower scores on one variable are associated with lower scores on the other. Let's talk a little more about direction of correlations that are indicated by the sign on the correlation coefficient. Here are some examples of positive and negative correlations. One example of a positive correlation would be examining the interaction between mother and child. Mothers who exhibit higher sensitivity tend to have children with higher self-regulation abilities. A football example of a positive correlation would be examining offensive player performance. Offensive players with fewer hours of football practice tend to have fewer points scored in games, and players with more practice tend to score higher in games. An example of a negative or inverse correlation could be examining children in timeout. So children with higher self-regulation abilities tend to spend fewer minutes in timeout. Another example from social psychology would be examining shyness. So people with higher shyness tend to have fewer romantic dates, and in general tend to have fewer social interactions. In addition to the direction of the correlation coefficient also tells us about the strength of the relation. A correlation coefficient closer to 0 tells us there's a weak relation between the variables. A correlation coefficient closer to 1 tells us there's a stronger relation between the variables. The correlation coefficient, R, for a perfect linear relation, which hardly ever happens in real life, would be -1 or +1. That is, the absolute value of the coefficient would be 1. When you have a coefficient of -1 or +1, this is considered a perfect relationship, and is the basis for this stats meme shown here. The dots form a line with a constant rate of change, in other words, a straight line. That's why it's called a linear relationship. The straight line can be in any direction, meaning high to low or low to high. Now that we know the basics of correlation, here's some additional information regarding databases. Basics. First, to compute the correlation, each person or case in your dataset must have a data point for both variables. In addition, we typically aren't trying to manipulate anything in this analysis. Because of this, we don't use the independent versus dependent variable terminology. The variables are just variables. Thus, it's different from analyses often used for experimental work, such as independent samples t-tests or ANOVA, where we assign people to groups, manipulate something so that it differs between the groups, and then measure the groups on a dependent variable and compare the means, and infer that the group differences are due to the thing that we differed among the groups. We often do that to infer causality. That's not the point with this analysis. If you ever heard the term correlation does not equal causality, that applies here. Usually in correlational analyses, we just measure people on two observed variables and see how those variables relate. As we'll see, we aren't trying to infer that X caused Y here. We just want to know if X is related to Y, and vice versa. This concludes the first lecture on correlations. In the next lecture, I'll describe how to examine correlation in scatter plots.